Assalamualaikum warahmatullahi wabarakatuh. We are from group 10, so we have studied and experiment the investigation of automobile exhaust gas driven diffusion absorption refrigerator. So I am Khairul Hakim bin Rashid, one of each group member. So for introduction, I want to tell you in that this experiment is using diffusion absorption refrigeration (DAR), which runs using any source of thermal energy. So in this experiment, we use using vapor absorption system instead vapor compression system, which is diffusion absorption refrigerant. So in this experiment, we using automobile internal combustion engine exhaust gas as an energy source. In the AR, liquid is compressed instead of vapor. DAR cycle also utilize triple fluids, namely ammonia, water, and auxiliary inert gas, usually hydrogen, where ammonia is used as a refrigerant and water as absorbent. So the aim of this study is to investigate experimentally the feasibility of constructing an automobile refrigerating system using DAR powered by IC exhaust gas and evaluating its performance. So the basic principle of this experiment, for the first one, the transfer of heat from a low temperature medium to a high temperature one requires special device called refrigerators. Then the efficiency of refrigerator is expressed in terms of performance (COP), denoted by COPR. Third one, the maximum COP of an absorption refrigeration system is determined by assuming the entire cycle is totally reversible. And the last one, absorption refrigeration system involve the absorption refrigerant by a transport medium. So that's all from me. Thank you.
Assalamualaikum and very good morning. My name is Muhammad Zaini Wahid. I will explain about schematic drawing. So the forming part of test rig, it will begin at a diffusion absorption refrigerator and will continue at an ICE as the source of heat in form of exhaust gas and continue at engine and cooling loads and finally end with measuring facilities. So this is the schematic drawing of test rig. So the exhaust gas heat exchanger will produce exhaust gas that divide into two parts. Some will go exhale into atmosphere and the remaining part will flow through a branch pipe utilized for generator heating. Exhaust gas that exhale to atmosphere known as main part. The branch tube will be inserted with generator terminal tube that carry exhaust gas that forming a heat exchanger. It will be insulated with 50 mm thickness of glass wool and covered with an aluminium sheet to minimize the heat loss to the atmosphere. Therefore, the amount of applied gas was adjusted by means of two regulator valves installed before and after branch pipe. So the engine and cooling loads. For variety of engine loads that using set of lamps connected to the engine during experiment. Cooling load that placed inside the refrigerator also use a set of lamps that installed in the refrigerator. So this instrumentation and measurement facility that have in test rig. So the first one is temperature measurement. It is the function of this is to show condition and record the output signal during the experiment. Secondly, the fuel flow rate measurement. This is to measure the fuel volume rate entering the engine. A calibrated tube was used. Finally, exhaust gas velocity measurement. An anemometer with accuracy of plus minus 2% will measure exhaust gas velocity at the outlet of both main part and branch pipe. Thank you.
Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Afiq bin Muhammad Nazim. So we move to the method performance analysis. For the method performance analysis, first we have the experimental process. Heat in the form of exhaust gas is supplied to the generator as the engine begins up following the beginning of heating process. To reach steady state, the process took almost 20 minutes. All temperatures were measured at various locations before and during steady state. The evaporator load will affect the duration of test run. This also depends on the input heat to the generator from the exhaust gas heat exchanger of the engine. The process to collect data will take 10 minutes. This step will be repeated for the same engine load and evaporator load for several times. 3 sets of experiments were done. The first set includes data collected from running the engine at 0 watt and varying the cooling load to be 0, 20, 40, 80 and 120. The second and third sets include data collected from running the engine at 500 and 1000 watt, respectively, with the same variation in the cooling load. For the experimental results, the temperature difference across the evaporator increases with the increase of the cooling load. Then, the theoretical COPs decrease with the increase of the cooling load, while the actual COP shows disagreement with the theoretical COP's behavior, as it increases with the increase of the cooling load. Then, the lower the generated temperature, the higher the actual coefficient of performance, and the lower the theoretical coefficient of performance will be. It was also found that it is better running with low engine load due to the excess heat available in the exhaust gas.
Assalamualaikum, my name is Zafarul Azfar bin Zamheri. I am from Group 10 and I will explain about performance calculation system. Okay, for the performance calculation system, I'm going to talk a lot about the formula used. So the first formula is about the Carnot efficiency of power generation, as you can see at the number 1 here. So this is the formula, Tg minus Ta over Tg. Okay. The next is Carnot COP of refrigeration cycle. This is the formula used in number 2, and by combining the formula number 1 and number 2, we can obtain Carnot COP of the plant. So this is the Carnot COP of plant after we combine the number 1 and number 2. And Tg, Ta, Te and Tc are generator, absorber, evaporator and condenser temperature respectively. Okay, next. Actual COP of absorption refrigerator. As you can see here, this COP can be obtained by dividing the evaporator load by the heat supplied to generator. Next, the amount of heat supplied by the exhaust gas to generator can be defined as this formula. This symbol is the exhaust gas mass flow rate. This symbol is the exhaust gas specific heat, and this symbol is the exhaust gas temperature difference across heat exchanger. Then we get this formula derived from the actual COP of absorption refrigerator. Next, by measuring exhaust gas velocities V and cross-section area of heat exchanger A, the exhaust gas volume flow rate can be calculated like this using this formula. The mass flow rate can be expressed as below, where ρ is exhaust gas density. You also can see it here. Thank you.
Warahmatullahi wabarakatuh. My name is Ahmad Rizza bin Abdul Malik. I will now present to you the suggestion to improve the system. For the first one, designing a computerized control system to optimize the operation of the plant by controlling the temperature as required and the engine exhaust mass flow rate required. For the second one, improving the heat exchanger efficiency by using materials that resist corrosion caused by the exhaust gas or using an anti-corrosion coating. For the third one, studying the effect of vibration on the system. For the fourth one, studying the possibility of the storing the heat available in the exhaust gas by heating a fluid storage tank that can be used as a temporary heating source when the engine is shut down. For the fourth one, constructing a multi-evaporator system to satisfy other refrigeration and air conditioning requirements in the passenger's cabin. For the final one, using other paths of fluid instead of water and ammonia and re-evaluate the performance of the system and get the other possible final result. Thank you.